first concept that you need to understand here is the concept of internal resistance. You know, resistance is offered by any circuit component when current flows through it. So when the current flows, so guys, yeah, I was telling you that resistance is because the fact that when charges or electrons are passing through any circuit component, they lose some of the energy. So just like any circuit component, like lamps, like heaters, they will take up some of the energy when electrons are flowing through it. So despite the fact that inside the battery there are chemical reactions which are taking place to provide energy to electrons, but electrons need to pass through or flow through these batteries as well. And when electrons will flow through these batteries, they will lose some energy inside the batteries. And you have a very good evidence of that. If you might have noticed, I mean, if you connect a battery to any circuit and you use battery for some time, then you will see that you will experience that the battery gets heated up. So definitely some heat energy is produced inside the battery as well, which means that when current flows through inside the battery, then charges will lose energy inside the battery. And that is because of the resistance of the battery, and that resistance of the battery is called internal resistance. There is resistance inside the battery. There's the resistance of the circuit component of battery as well, and that resistance of the battery itself is called the internal resistance. So guys, I mean, as I said, that batteries always have internal resistance, but in some cases you ignore them, in some cases you don't ignore them. So most probably they will draw a circuit component of battery like this, which is an indication of the fact that you're not ignoring the internal resistance of the battery. So though this internal resistance exists inside the battery, but you just, for the sake of representation, you just make it right next to the battery. So if you make a battery component like this, where you have a broken box in battery and a small R resistance right next to it, then that means that you are not ignoring the internal resistance of the battery. And if that happens, now what you need to understand is that if you're not ignoring the internal resistance of the battery, then there are two types of voltages that appear across the battery. Because if there is an internal resistance and the drop would occur on that internal resistance or across that internal resistance, that drop would only occur if current flows. So that means if you look at these two diagrams, then you'd be able to identify that, sir, over here, the switch is open, and there's no current flowing. And since there's no current flowing, so there will be no drop across the internal resistance. But when you close the switch and the current starts flowing, so that means that the drop across the internal resistance would occur. So across the battery, you have two types of voltages. One, which is without the drop across the internal resistance, that is when the battery is not supplying current. The other one, when the circuit is closed and the current is flowing, and that is when some drop would occur across the internal resistance and the voltage that appears would be lower than the situation where the switch is open. So the voltage without the drop across the internal resistance is called EMF, represented by E. And the voltage after the drop is called terminal potential, and it is represented by V subscript T. So you would be coming across two terms with situations where you have to consider internal resistance of the battery, and that is that there is a term of EMF. That's when there is no drop across the internal resistance, and that happens when the switch is open and battery is not supplying any current. So the voltage that appears across the battery when battery is not supplying any current is called EMF, and the voltage across the battery after a drop across the internal resistance is called the terminal potential. If you measure the voltage across the terminals of the battery here, or you measure the voltage across the terminals of the battery here, you'll get different values. The first thing you need to understand is that you'll get a higher value here and a lower value over here. Why would you get a higher value here? Because there's no drop occurring across the internal resistance. Why is there no drop occurring across the internal resistance? Because there's no current flowing and voltage drop is only V equals IR. If there's zero current, there's no voltage drop. But when you close the switch and the current starts flowing, then there will be drop across the internal resistance. And after that drop, a new voltage appears across the ends of the battery. And that is called the terminal potential. So the voltage drop is how much it decreases. And then after that decrease, the voltage that appears across the end of the battery, that's called terminal potential. Like let's say the EMF of the battery is 10 volts. But when you connect it to a circuit, then the battery doesn't show 10 volts. The battery shows 9.2 volts. So that means 0.8 volt drop across the internal resistance of the battery. So if originally it was showing 10 volts, but after connecting it to a circuit, if it's showing 9.2 volts, so its EMF is 10, its terminal potential is 9.2, and the drop across the internal resistance is 0.8. So I mean, in this kind of situations, guys, you have two resistances. One is the resistance of the battery, and the other one is the resistance of the circuit. So we represent resistance of the battery, which is called internal resistance by small r, and the resistance of the circuit by capital R. So you would say E minus IR, because IR would be the voltage drop across the internal resistance, and that would be, this is the actual EMF of the battery, this is the voltage drop across internal resistance, and after that what appears across the external resistance is terminal potential. So IR is the terminal potential voltage across the external road. I into small r is the voltage drop across the internal resistance. And E over here represents the EMF of the battery. A lot of situations. So total EMF is equal to sum of two voltages. One is the voltage drop across internal resistance, and the other one is the voltage drop across the external resistance. This is something we've been ignoring up till now, but we won't be ignoring it anymore. I mean, in questions where we have to consider internal resistance. And guys, the other thing is, I mean, the derivation of it is very, very mathematical. You have to use differentiation to prove that, which we don't really need to use that as our syllabus content. But what we need to understand is that if we have a variable resistor connected over here, and we will identify the power dissipated across the external resistance while varying the external resistance. So I'll get the maximum power when the external resistance is a value that's equal to the internal resistance.